recap. So what we learned yesterday. So we learned about the parametric test. So and we know the hypothesis setting, null hypothesis and alternative hypothesis. The null hypothesis tells the hypothesis of no difference. Alternative hypothesis tells the hypothesis has a difference. And the p-values, if the p-value is less than 0.05, there is a significant difference. If the p-value is greater than 0.05, there is a no difference. And if you just have a flowchart of this, I just borrowed this from a book, very nice data analysis book, where the one sample is there. We for the one sample we either use Z test or the T test. For the paired sample we use paired T test. If there is a two samples, for the unpaired we use the T test for equal variance, T test or unequal variance. If more than two samples, if anything comes more than two samples, we use ANOVA, and for getting the relationship we get the Pearson correlation and linear regression. So till two samples we use paired t-test z-test, a one sample t-test. If you want, if you get more than two samples, then we can use ANOVA. But any number of samples, it doesn't matter, we can use ANOVA every time. Because I will tell, because we had a t-test, so why there is a need of discovering ANOVA? I will come to the point what was the need to discover ANOVA. So this is the non-parametric test. When normal distribution, when the distribution of the data is not in the normal condition, is not normally distributed. If there is a skewness, like kurtosis or left skewed or right skewed, then we use this kind of test: chi-square, Kruskal values, pixel skin, or Spearman rank correlation. And what are non-parametric tests? So non-parametric tests are distribution-free statistical tests. It doesn't matter if the distribution is normal or not normal. It do not assume any normality. Is suitable for ordinal, nominal, or skewed data, and used when parametric assumptions are violated. Here it comes the first, the chi-square test. The chi-square test is the test association between categorical variables. It's association to see. It's a test to see whether the given observation is in association with a certain ratio or with a certain trend. Whatever the observation we found, whether this is in association with a certain trend, whether we need to check it with yes or no, we do the chi-square test. It's also called as a test of independence or test of goodness of fit. So one thing you need to note down here, when the p-value is less than 0.05, this alpha value, there is a significant association exist. And if it is more than 0.05, the variables are independent. There is no significant association exist. So Wilcoxon signed rank test is also a non-parametric test. It's an alternative to paired t-test. Paired t-test is a parametric test. So it's an alternative to paired t-test. It compares two related samples based on the ranks of differences. This calculates the ranks of each variable and they calculate the differences in the ranks. And it's also same thing, significant p-value, there is a difference. There is no significant, there is a more than p-value, there is a no difference. And Kruskal values test. See, these are all group comparison tests. This is the comparison of means, something similar to the t-test. The Kruskal values test. Sorry, somebody want, I don't want to let down. Yeah, the Kruskal value test. The test tells is a non-parametric test alternative to one-way ANOVA. So if you have more than two samples, then you can do Kruskal values test. It's an alternative to one-way ANOVA. It compares three or more independent groups. It's also based on the rank. The significant p-values, at least in one group, differs. The p-value is less than 0.05. There's a significant difference. And if it is more than 0.05, there is no difference. And we also speak about the post-hoc test. The post-hoc test is after doing ANOVA or PAT test. We need to check whether the difference between two means or difference between two variables is significant or not. Again, there is a test called the post-hoc test. There are different post-hoc tests called Turkish test, Fisher's LSD, DMRT Duncan multiple range test, something like that. The Spearman rank correlation. I told when when the when the scatter plot doesn't look like a linear, it doesn't look like a proper correlation curves. If there is a monotonic or there is a polynomial kind of graphs, then there it comes the Spearman rank correlation. Because if the scatter plot is not looking like linear correlation, where there is no linear, where there is no proper association, you can't see proper association, then the Pearson correlation doesn't work. Then we need to go for the Spearman rank correlation. It also ranges from -1 to +1. So advantages of non-parametric test is a pure assumptions applicable to diverse data, any kind of data, robust to outliers, and simple interpretation. There is no much calculations in this. So this is in slide. So for the one sample, we go for one sample median test, and for the two samples, paid Wilcoxon or Mann-Whitney, that's also a kind of Wilcoxon test. For more than two samples, we go for Kruskal-Wallis test. And for the relationship, it goes for Spearman rank or linear regression. Similar to, yeah. So some people were asking the type 1 error and type 2 error. These are very important. So this will be asked in many examinations, and we should also very aware of these kind of errors while we are calculating the data. So type 1 error. So there is a two hypothesis. One is a null hypothesis, one the alternative hypothesis. In the null hypothesis, there is a no difference. In alternate hypothesis, there is a difference. So when type 1 error occurs, it occurs when we fail to reject null hypothesis when it is false. So when the null hypothesis, when there is a no difference, can you able to understand? It's a false positive. It's, it's, it's a kind of false positive in the type 1 error where you can see it here. It's a rejecting null hypothesis when null hypothesis is true. When the null hypothesis is true, so suppose there is no difference, but we reject null hypothesis. We consider there is a difference. We accept alternative hypothesis. The type 1 error is a false positive. This is a very dangerous error. Though there is no difference, we consider there is a difference. Then it's a type 1 error. As simply I can say that if the wheat yield is giving, if the best stable wheat variety yield is 15 ton, and the local check is also 1510, and there is no difference between 1510 and the 1510 is same. So this is null hypothesis. When there is a null hypothesis true, even though we need to reject the null hypothesis, we need to say that when the null hypothesis is true, we need to say that there is no difference, but we consider there is a difference. There is a difference between local check and the best variety. So it's just like rejecting null hypothesis when null hypothesis is true. That's a false positive. So when null hypothesis is true, we are just rejecting it. We are just rejecting the null hypothesis and accepting the alternative hypothesis. So it makes the false positive. It makes even there is no difference, we consider there is a difference. It causes a huge error. This is type 1 error. And the type 2 error is failing to reject null hypothesis when alternate hypothesis is true. This is false negative. So type 1 error gives false positives and type 2 error gives false negatives. So when when alternative hypothesis is true, we need to reject null hypothesis, need to accept the alternate hypothesis. But what we do, we fail to reject the null hypothesis and accept the null hypothesis again. Though there is a difference between the best variety and the local check, we consider there is no difference. So this is false negative. This is type 2 error. And the type 3 error can occur when a researcher has chosen to use one tail test. Yesterday I told there's a one tail test and a two tail test. So there can be possibility less than or greater than. So if you just consider only less than, if you just consider only greater than, this is a one tail test. So one tail test can cause type 3 error. So there are three errors: type 1, type 2, and type 3 errors. So type 1 error cause false positives. Type 2 error causes false negatives. So this is an easy way to understand type 1 and type 2 error. Is rejecting the null hypothesis when it is actually true. So we are rejecting the null hypothesis when it's actually true. So we are accepting the alternative hypothesis. In type 2 error, failing to reject the null hypothesis when it is actually false. So that failing to reject null hypothesis when alternative hypothesis is true or itself is a false hypothesis. So this is false positives and false negatives. So these two things is might confusing for you, but you need to go through this again and again. And if you start reading the literature, it will be very easy. So type 1 error cause false positives. There is no error, there is no difference, but we consider there is a difference. Type 2 error causes false negative. There is a difference, but we consider there is no difference. So next is ANOVA. So why ANOVA? We can ask why ANOVA. We have a T test and we have a G test. So if there is more than two samples, two variables, we can do multiple T test. So why we need to do ANOVA? We can do one T test for the one pair, another two test for the another pair, another T test for the another pair. We can do multiple T test. But the problem is each t-test, we calculate the level of significance. That's alpha is 0.05. There is the 5% of the error will be there. That's why the level of significance is 5%. So for making each t-test, there is a 5% error. And if we compare more than three variables or more than two variables multiple times, for each comparison there will be 5% of error. For another comparison, there is a 5% of error. There are another comparison with the 5% of error. If we merge all the errors, the error becomes more and more. It's more than 5%. So that's why we are increasing type 1 error here. The false positive errors is increasing. So that's why we need a test where one test can compare all the tests. One test can compare all the variables and can reduce the type 1 error. That's why the ANOVA came into the picture. So ANOVA is a one test for all the groups. ANOVA is analysis of variance. Compare all groups means simultaneously. It tests the null hypothesis. All group means are equal or not. It also controls the main important. ANOVA controls type 1 error rate. How I showed you before in the last slide. And ANOVA is also combined with the post-hoc test. I told post-hoc test is a Tukey test, Fisher's LST test to see whether the significant difference is there or not. ANOVA tells there is a significant difference. But if we compare two variables to see how much significant difference is there or not, we need to use the post-hoc test. So it's a multiple t-test. The post-hoc test is similar to multiple t-test but less type 1 error. ANOVA is a single t-test. So rather than doing multiple t-tests, we use a single test to control the type 1 error. It's more than two groups. And this is the ANOVA table. It has a source of variation, that is between groups, within groups, error and total, sum of squares, degrees of freedom, mean sum of square and the F values. The sum of square is calculated uh, by minusing, it's a square deviation, just like a variance, square deviation of the mean to the each value. And degrees of freedom is calculated from number of variables minus 1. The mean sum of square is calculated by sum of square divided by degrees of freedom, and F values are calculated by between group mean sum of square divided by error sum of square. So there is a two kind of ANOVA. There is a one way ANOVA, two ANOVA. When there is a one variable, only genotype is the variable, and we are seeing the yield, then we go for one way ANOVA. One way ANOVA means only one variable. When there is a two way ANOVA, there is two variables. Like one is the genotype, one is the irrigation, or one is the treatment, drought or conventional breeding. Conventional, whether it's a drought or control. So we have a genotype as a one factor and irrigation as another factor, or countries as another factor. Whatever the example data we took yesterday, there was a genotype and there was a countries. So we have a two factor. Then we go for two-way ANOVA. If it is a one factor, it's one way ANOVA. If two factors, two-way ANOVA. So in a nutshell, so one-way ANOVA is the one factor, two-way ANOVA is the two factor. So hypothesis tested is group means equal. Here group means equal plus interaction effect also will come into effect. So this is for today. But today, after explaining this, I will go to the R studio, and by today we're gonna finish all the required theoretical things and all the stuffs. Tomorrow I will keep separately for the Excel. So some of you are not very much friendly with R Studio, you are feeling difficulty. So there are many things we can do in Excel also. So tomorrow whole session I can teach you doing ANOVA, doing correlation, doing some other stuffs in Excel. Today I will show you how to do analysis in R Studio. Is it okay for you guys? Or you want to spend whole time in the R Studio? So there are many stuffs. There are many stuffs you can also do in Excel, because everyone is not friendly with Excel with R Studio. So I'm going to show in Excel tomorrow. So today I'm going to show with R Studio. Is it fine,
Yes,
Nikhil?
sir. Yes, sir.
Yeah, oh, great. Thank you. So still now, do you have any doubts in type 1 error or type 2 error, false positive or false negative? What is false positive? What is false negative in any non-parametric test? Nikhil, do you have any doubts? Kanaka? All
No,
right, then
sir.
it's great. So I'll just go for the R Studio now. So I already shared whatever the files we need today. So I already shared with you guys.